Well, good morning. This is 11:37. I'm 7 minutes late getting started. I've been waiting for someone to come in the room, but so far nobody has. So I'll go and get started as is. I was working on just getting my attendance up from the other two classes while waiting for someone to come in. A book bag is in here. I assume one student has been here, but I don't know right now which one it is. I'm guessing, I don't know whose book bag that is. It may be one left over from the last class. Wait, here's an ID on it. Oh, that's Terrell's. Okay. So I assume Terrell is coming because his book bag's in here. But at least his book bag's here. All right, so we're beginning Chapter 2. We finished Chapter 1 last time. I gave you the test, take-home test. I hope you're making progress on that. Chapter 2 is matrices, as if we have already been doing matrices. Well, this time we're going to do things like operations of matrices, properties of matrix operations, inverse of a matrix, elementary matrices, and applications of matrix operations. So let's get started on operations with matrices. Okay? First, and this is pretty simple, straightforward, a few things about matrices. Standard mathematical convention to represent matrices in any one of the following three ways. The first, we can name it, and the typical names are capital letters. A, B, C. Those are typical names of matrices. Okay? Second way is to represent a to list a representative element in brackets, like this one, A, I, J. Okay. Now we'll talk about a few things about that. Okay, first, if you had that, you need to have something else. The book just lists this, but what it means, then you would follow this by 1 is less than or equal to I is less than or equal to some value M, okay? And 1 is less than or equal to J is less than or equal to N. This would mean this is an M by N matrix, M rows, N columns, and the I's and the J's count through these various things. That's one way to represent a matrix, just by that one thing. Or you can actually list all those individual elements. And this is what we've been doing typically. A11, A12, A13, dot, 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 A1, N. A21, A22, A23, dot, 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 A2, N. A31, A32, A33, dot, 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 A3N, dot, 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 down to AM1, dot, 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 down to AM2, dot, 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 down to AM3, and then dot, 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 everywhere, dot, dot, AMN. That is listing every element, not the IJ. But you see, these are saying the same things. This is every thing. I equal 1 to M. There's your A11, A12, A13, all the way up to, A11, A21, A31, all the way up to AM1. Then go to the next J, A12, A22, A32, all the way up to AM2. List them every one that way. Whichever you start with, listing all the way through. Those represent the same thing. Certainly the easiest way is just give it a name, A. Okay. Typically if we had another matrix B, then you would name its elements little b ij or little b1, 2, or whatever. Okay. Now, if that's how you list a matrix, It says, as mentioned in Chapter 1, matrices in this text are primarily real matrices. That is, all the entries are real numbers. You can have complex numbers, but we're not going to be messing with complex numbers. I don't think at all, but what little we do, it'll be pretty minor. Okay, so the subsection here is equality of a matrix. What makes two matrices equal? Here's the definition. I'll start on a clean page so you can get it all written for you. Two matrices, okay, A, and we're going to use the short notation Aij, and B, which is little b ij. Now, they are equal. This is equality of matrices. This is what we're doing. When they have the same size, okay, we'll call it m by n, okay, and a sub ij is equal to b sub ij for every 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n. Okay? Every one. Every ij is identically the same. So when they say same size, m by n, m by n, m is the number of rows, n is the number of columns. Okay? So a 3 by 2 would be 3 rows, 2 columns. Now just because that has the same number of entries as a 2 by 3, they can't be equal. They have to be exactly the same size, 3 by 2. Or both of them have to be 2 by 3s. But not only do they have to be the same size in the same order, they have to have identically the same elements. A11 is the same as B11, A21 is the same as B21, yeah, all the way down. Every entry has to be precisely the same. Okay? If they are, then the two matrices are equal. Okay? So here is example 1. Consider 4 matrices. Here's matrix A. This time we're going to list them all. 1, 2, 3, 4. Pretty creative matrix. Okay? B is 1, 3. Always tend to do that, or often tend to do that. I don't know why. When I just have 2 entries, I'll want to put a line like in a fraction or something. I don't know. 1, 3. Okay. C is also 1, 3. All right. Good to see you. I saw your stuff here. Thank you. I know you were on the other end of the conversation I had with Ms. Chisholm, but you have got.
She said she's going to check with Vice President.
Right.
Yeah. And she said give it a couple of days and come back if I can call you within those days. Right. And I'll see what's going on.
Okay. Well, I was going to ask, I told you before that you weren't showing up on the no-show report.
Yeah.
As being, but you've gotten all that taken care of.
Yeah, I got all that taken care of. I had to wait for a trio. They normally help me out with my remaining of my tuition.
Oh, I see.
Yeah,
okay.
so I had to wait for them to process the.
I
guess it was pending when you seen that I wasn't showing up.
Well, yeah, I mean, you always have shown up on the roll when I'm doing attendance, but when I went to do the no-show report, that's the one you weren't showing up on. And that is the official attendance, meaning everything's covered. Your attendance in class, yeah, people can still be in class without having finished everything up to a certain point. They haven't told us, they never tell us when that point is until they say, it's this Friday, you know, or
Right,
something like
right,
that.
right.
So we haven't heard when it is yet this time. Okay. All right, I'll turn on the projector now. And I'll also read an announcement. I thought I wouldn't read to an empty room, but this may be something you might be interested in or not. I don't know. You may have heard me talk in past years when you've been in my class about Norse fellowships or scholarships. The Norse program is sponsored by the National Science Foundation. So typically they have enough money, okay? UAB had a Norse program. University of Alabama had a Norse program. But they're usually 3 to 5 year grants. So it could be theirs are expired now. I don't know. It's been a while since we've sent anyone there. But A&M now has one. They've just got one, it sounds like. They've launched their AAMU North Scholarship website, okay? We are a partner with them, okay? And so they're looking for students, especially students in STEM type fields, science, technology, engineering, and mathematics. And you fit in that category like a glove, okay? And what the thing is, they'll provide you learning opportunity for a summer. Now, some of the programs have been as short as 3 weeks, and some of them have been as long as 9 weeks. I don't know what A&M's is. Okay. Pardon me?
I can pick up my test.
Okay. I'm sorry?
And for the other class, differential equations.
I don't have it up here. It's down in my office. Okay.
Yeah, I'm trying to finish my essay.
Pardon me?
I have to finish my essay for English. That's why I can't stay.
Finish what? I can't hear you.
I had to finish my essay for English.
Oh, I see. Okay. All right. And how it is here? Okay. I was just announcing about the North scholarships. AAMU, Alabama A&M University, has just gotten into this. And basically, my understanding of the whole program, I know some things are probably different from the different schools, but the main purpose of it is to recruit good science, engineering majors, math, majors, and expose them to opportunities teaching math and sciences. Now, when I say sciences, it's mostly chemistry and physics. Usually they don't do biology because they have plenty of good biology teachers. But boy, in our K-12 system, we are way short of good math and science teachers. I mean, they are few and far between, and they usually have people teaching those subjects that aren't really interested and may not even be qualified to teach the subject. So they're really trying to encourage people to consider teaching. What's that?
The city need statewide, they need to raise the salary of the teachers.
Yes, absolutely.
Now the younger generation, they're looking at how the living cost will be.
Right.
They say this is not gonna cut it unless you have a partner in your household. It's not gonna be the income from the school not gonna cut it.
Right.
So no one will be say, oh, you know what, I'll sacrifice this to go into. So we passed that age, so they need to update. Need to, we love to teach. Me personally, I would love to teach, but I'm not gonna be homeless and teaching, so it's not gonna cut it.
Not gonna what?
I'm not gonna stay homeless and teaching, so that's not gonna cut it. And the only way I won't be homeless is if they pay me enough to stay in the house. So,
and that is an issue all of us are well aware of, I guarantee. But they're still trying to offer these incentives to get people to at least consider it. Because some people may find out they really don't like engineering or don't like this, that, and the other, and thought, well, but I can teach, and we need those kind of minds that can do the stuff, and for people to consider it. You're right, they need to get the salaries up. And
they're raising taxes all the time. Right?
yeah. See, I married money, so I can do whatever I want to. So. Yeah. So, anyway, if you want more information, you've got more information. Check your emails, because this came to me, but it also came to all students at students.lawsonstate.edu. Okay, it's there, and there's links. You can find out all about the program. Spread the word on it too, because it's really a good program. They pay you a good stipend to do it. They provide room and board usually. I don't know about A&M. I assume they're going to do that. They pay you transportation to get to campus and get home one time. They don't do it for every weekend or something like that, but they do pay you transportation to get there and back once. It's a good program, and you learn lots of stuff. You get to experience lots of research. You get to experience teaching and tutoring. It's really a really fine program.
Would that be considered like an intern?
What's that?
Would that be considered like an intern?
Yeah, they'll pay you money, to do it. I haven't read the details, so I don't know what the stipend is at A&M, but generally it was pretty good. It's probably not what you would get as an intern at Mercedes or somewhere, but if you don't have a job, it's better than no job, for the summer. It's just a summer thing. It's either 3 week, 9 week, 6 week, something like that. So look at the details, see what it is, see if it fits. And if it is, consider it. All right. We're doing example 1 on page 40. We're just starting chapter 2, matrices, and 2.1 are operations with matrices. And the first that we did was, what do we mean by two matrices being equal? And they said list these. So here's the fourth one. D is equal to 1, 2, x4. All right. Now, the question is, are any of these matrices equal?
Will A and D be equal?
A and D may be equal on what condition?
If X was 3.
X was 3, or it could be 6 halves, or it could be, 12 divided by 4. It could be square root of 9. Yeah, as long as it has the same value as 3, then they would be equal. How about B and C? Those have the same values, don't they? But they're not the same size. B is a, what size? Row by column. 2 by 1, C is a 1 by 2. Not the same. See, two matrices to be the same, they have to be precisely the same size. M by N. B is 2 by 1, C is 1 by 2. Those are not the same, even though they have the same elements, but they're not in the same places. Okay? A and D could be equal if X is equal to 3 or has the same value as 3 in whatever form you want to put it. Yeah, that may be. But if X is not 3, 3.000000001, nope, not equal. Have to be precisely the same values. Okay. Now, a couple of nomenclature things. B is called, a couple things. A and D are both called square matrices because they have the same number of rows as columns. Okay. B is called a column matrix because it has only one column. Both of the elements are in the same column. C is called a row matrix. Now, both of these have another name. B could be called a column vector. C could be called a row vector. When one of your dimensions is 1, okay, then you can name it either a column or a row, matrix or vector, either one. All those names are the same. Okay. Now, Another thing that we're not going to do for a long time, but it could be done, is this matrix A could be defined as, okay, let me write this slightly different way, okay, even slightly different from what the book is doing, because this is another way to write it. I don't know. B, and I'm going to do A2 here to be 2. There, I've done it again. I do this every now and then. It just drives me nuts. I'm used to writing fractions, so I put a bar, and it's not a bar. If A2 is a column vector or column matrix 2, 4, B is already 1, 3, then you can, and this is called partition into B partition with A2. Okay. Now, when they bold things, I generally will put a vector symbol over it, because it is a vector. And you could put the brackets around this if you wanted to. I'm not used to putting brackets around B, but you could do it. It's the partition of B, which is 1, 3, and A, 2, 4, and that becomes 1, 2, 3, 4. Okay. Now, they tell you this, they do it, they go through these steps, equal 1, 3, 2, 4, and then they tell you that's the same as B, A2. If they put a bold, I can't write bold, so I usually put a vector over it in a minute. Okay. They do that, then we hardly use partitioning. We will at some point in the future, but not very much. So I don't know why they even mentioned it here, but they did. And it's true. There's nothing wrong with it. All right. So that was equality of two matrices. Now let's do the addition of two matrices. Okay? It starts the same way the other did. If A is equal to matrix Aij, has elements Aij, and B is equal to the matrix that has elements Bij. Okay? If these two are matrices, okay, of size, it's going to come back. And do they put this? Sometimes they put it and sometimes they don't. M by N. Okay? See, last time they put that in parentheses, this time they don't. I never know which way they're going to write it. Now, what does that mean? They have to be identically the same size. Okay? M rows, N columns. Have to be in order to add them. If they're not the same size, you can't possibly add them. Okay? If that's the case, say again? Okay, if 0 is one of the elements?
If they're not the same size, can you add the zeros to,
No. You can't change a matrix. I think I know what you're saying. A matrix has to have every element in the rows and columns filled in. You can't have blanks in a matrix. You can have zeros in it, but you can't have blanks. But if A was an M by N, let's say a 3 by 4, and B was a 4 by 3, you can't add them. Or if it was a 4 by 2, you can't add them. You can't add another row of 0 because that's a different matrix. Okay? So, yeah. You can't go in adding anything to make it the same. They have to be what they are. Okay. But if these are the same size, then the sum is hopefully just what you would expect it to be. It's also N by M matrix. M by N, I said it backwards. Wrote it right, almost. Said it backwards. Oh, wrong. Okay. And it's given by, okay, A plus B. These are how you represent matrix, capital letters, A plus B, and that would be the element Aij plus Bij. Okay? Now I'm sorry. I knew that didn't sound right. Aij plus Bij in the same bracket. Okay. And what that means is the sum is the same size, M by N, and each element, you take the first upper left element in A, add it to the upper left in B, that's your upper left in A plus B. And then for every element, you have to do exactly the same elements you're adding together. That gives you that. That's why they have to be the same size. If the one with more columns or more rows than the other, or fewer than the other, you'll have some left over, and you can't have any left over. They have to be the same size. Okay? The sum of two matrices of different sizes, undefined. You just can't do it. Don't even try. So I think I'll go to a clean page to do the examples. Okay? So here's the A one. Negative 1, 2, 0, 1. I'm going to try to add that to 1, 3, negative 1, 2. Okay, first question, can you even do that?
Yes.
Yes, you can. Daniel's here. Okay? And what would be the result? What size?
It's gonna be,
Say again?
it's gonna be 2 by 2.
2 by 2 also. And what would be the first entry?
It's gonna be
0,
0, 5,
5, negative 1, 3, right? Yeah. Okay. Perfect. Okay. Yes, you can add those together, and that's what you get. Okay. How about this? 0, 1, negative 2, 1, 2, 3, 0, 0, 0, 0, 0, 0. Can you add those two together? It'll be the very same thing you had at first. 0, 1, negative 2, and 1, 2, 3. Okay? Now, that leads to another concept we haven't gotten to yet, but I'm going to say it now because it's here. The zero vector, whatever size it is, if every element's 0, that's called the additive identity vector. So if you add that to a vector of the same size, whatever vector is matrix exactly the same size as this, then you'll get the same result. You'll get this because you're not adding anything to it. Pretty obvious. But that's just like in addition of real numbers, 0, the number 0 is the additive identity element. You know, you add 0 to 17 million, you get 17 million. You don't change the value at all. Okay? What's that?
Even how you add that 0.
Well, yeah, you can't just plug it on at the end. Right? I got to watch him. Okay. Okay. Now, here's the C1. 1, negative 3, negative 2. We're going to add that to negative 1, 3, 2. And what do you get there? Can you add those two? Yes, you get 0, 0, 0. Now, anytime you have this, this is called the additive inverse of that. And this is the additive inverse of that, because when you add the two together, you get the 0 vector of the proper size. Okay? Just like negative 3 plus 3 is 0. That means negative 3 is the additive inverse of 3, and 3 is the additive inverse of negative 3. Same thing here with matrices, or with, these are happen to be vectors as well. And let's do D. 2, 1, 0 plus 4, 0, negative 1, and add to that 0, 1, negative 1, 3. What's the result of that? Cannot do it because they're not the same size. Okay, even if I can't write. So 4, okay. It doesn't matter. They're not the same size. You cannot add them. That's undefined. You can't do it. You can't add another 2 zeros at the end of that one and say you can do it. You can't do it. Those are two different vectors, different size vectors. You can't add them. All right. Now, we're not going to do all these. Not now, anyway. There are several ways you can multiply vectors. Okay? We're going to do the easiest one first. Okay? If, oh, and by the way, a number, just a pure number, no brackets around anything, just a number, that's called a scalar. Okay? Now, if you've got an array of numbers, that's called a matrix. If it's a columnar or row array, that can also be called a vector. Okay? So you have these three terms: scalar, matrix, vector. Matrix is any combination n by m, of numbers, an array of numbers. If it's a single column or a single row, it can be called a vector or a matrix, either one. But any element in any column or row, that is a scalar. That's just a number. Okay. So when we're talking about scalar multiplication, that's taking a matrix or a vector and multiplying it by just a number, not another matrix, not another vector. Okay? So if A, okay, is defined to be, just like we've done before, A sub ij, okay, is an m by m matrix and C is a scalar, okay, meaning just a number, then the scalar multiple of A by C, little c, is also an m by n matrix. You don't change the size of the matrix by doing this. And here's what it is. C times A is equal to C times every little element that's in A, Aij. You could write it on the outside, but that means that every element inside is multiplied by C. Okay? Every one. That could be a 7 by 14 matrix. Every one of those elements is multiplied by C. Okay. Now, another concept while we're here is this one, negative A. That C one that we did before, the first matrix or vector that we did, was added to its opposite. All right, here's coming out to be a fairly well attended class today. We're still missing Vince and Gordon. I've seen Jordan in a while. I saw Catherine the other day. She came to class, I guess it was yesterday. And Vince, I know he was moving and had some other issues going on, but sounds like there were some problems too, so hopefully he'll be able to get back. So negative A represents the arithmetic opposite, meaning you negate everything. It's the same as negative 1 times A, which by this definition is take every element, I, A, I, J, every one, and negate it. If it was a 17, it becomes a minus 17. If it was a minus 34, it becomes a 34. You negate each element individually, okay? And that's called the, this is a scalar product. It's just a scalar is negative 1, okay? Now, if A and B are the same size, then A minus B, this is subtraction, is the same as A plus the minus of B. I'll put that in parentheses. Okay, they don't. No, they do. Well, they actually do this. Equal A plus negative 1 times B, which is, I hope, what you would expect anyway, is that the subtraction of two matrices is the first one added to the opposite of the second. That's how we do subtraction of all signed numbers, so matrices are included with that. All right, so let's do example 3. Any questions so far? This is all pretty straightforward and hopefully pretty close to being self-evident. So let's say we have two matrices. Here's matrix A. 1, 2, 4. Negative 3, 0, negative 1. 2, 1, 2. Used to be a defense we ran in basketball. Okay? Here is matrix B. 2, 0, 0. 1, negative 4, 3. Negative 1, 3, 2. Okay. All right. With those two, goodness gracious. After the last class, I was so hungry I was going to go down to the office and grab a granola bar. And a student came in and he needed this and he needed that and he needed something else. By the time I got him everything he needed, going through stacks of paper and stuff, I looked down and I was a minute late. So I didn't get to eat anything. And I'm so starving right now, I'm almost dizzy feeling. All right. They asked us first to find 3A. What would 3A be? You tell me. 3, 6, 12, negative 9, 0, negative 3, is that what you said? Yeah. Next. 6, 6, okay. So there's 3A. Well done. Wait a minute, yeah. What's that? You what?
I lost how they got it.
Okay. Remember what we said, if you do a scalar multiple by a matrix, that means you multiply every element in the matrix by this. So there's your matrix A up there. So that'd be 3 times 1 is 3, 3 times 2 is 6, 3 times 4 is 12, 3 times negative 3 is negative 9, 3 times 0 is 0, and 3 times negative 1 is negative 3. 3 times 2 is 6, 3 times 1 is 3, 3 times 2 is 6. Every element gets multiplied by that. Okay? Now, second one is what in the world is minus B? What would that be? Negative 2, 0, 0, negative 1, 4, -3, 1, -3, -2. There we have that. Now, C, this is A, this is B, and there's C. C says, what is 3A minus B? What would that be? Well, here's 3A, and there's minus B, so you merely add those two together, right? And what do you get? 3, okay, it's not minus and minus 2, it's minus B. Minus B is this. So it's the same as 3 plus a negative B. Okay? So that would be 1. Okay. 6, 12, negative, no, 10. Negative 9, negative 1 is negative 10. Okay? 4, negative 6, 7, 0, 4. Perfect. Let's see how the book did. 1, 6, 12, negative 10, 4, negative 6, 7, 0, 4. Perfect, perfect, perfect. Okay. That's what we mean by scalar multiplication. Multiply a number by a matrix. Multiply every element in that matrix by that number, that scalar number. Okay. And of course, vectors would just be one column or one row, and you multiply each by that too. All right. Now, though, we're going to do matrix multiplication that's matrix by matrix. And this is a lot different, okay? It's its own kind of technique, okay? And they start by giving you a sample problem, and hopefully you can see the connection of what's going on there. What you have is a football stadium. It only has 3 sets of stands. One on the south end, on the south side, one on the north side, and one on the west end. Okay? So I will do that. South stand, north stand, and west end. Okay. That's what each row represents. What's going on, the concession stands on the south stand, concession stands on the north stands, and concession stands on the west stands. Okay. They're selling 3 items at each place. They're selling peanuts, they're selling hot dogs, and they're selling soft drinks, which this is a Yankee book, they call them sodas. Okay. Well, I've heard them called sodas too. That's so Yankee sounding to me, sodas. They're Cokes, aren't they? Okay. And down there, everything's a Coke, whether it's a Coke or not a Coke, it's a Coke. Give me a Coke. What kind you want? Oh, Sprite, that's fine. All right. And this is the number that you've sold. On the south stands, they sold 120. On bags of peanuts, 250 hot dogs. Those people were hungry. And 305 sodas or drinks. Okay. On the north stands, they sold 207 bags of hot dogs. Only 140 bags of hot dogs. And 419 drinks. Okay, and on the west stands, must be a pretty small stands there, only sold 29 bags of peanuts, 120 hot dogs, and 190 drinks. All right. Now, it just happens to be we also know the cost of these, the selling price. It was $2 for the peanuts, which is really a ripoff. $3 for the hot dogs, even more so, and $2.75 for the sodas. What a rip! Okay. Now, if you're wanting to determine what your total intake was from that, because this is dollar amount, selling price, that's what that last row is, what you do is multiply the number of bags of peanuts by their price, number of hot dogs by its price, and the number of these sodas by its price, and add them together. And that's how much revenue the South Stand got. So if you did this, that's how you would do, and this would be this is the selling price. Okay, this would be your total revenue, and this would be for South Stands, North Stands, and West Stands. Okay? So if you did that, 120 times 2 would be 240, plus 750, plus, then somebody else will have to multiply 305 by 275. I can't do that in my head. That would be how much you got on the south side. They have here is 1828.75. Did anyone do it? What's that? No. You do that South Stands, okay? South Stand, 120 for each bag of peanut at $2 a bag, $2.50 each hot dog, $3 a hot dog, and 305 sodas sold for $2.75 a soda. And when you do those and add them up, that gives you how much you made on the in the South Stands, right? In the North Stands, you do the same thing. You sold more peanuts, but they weren't as expensive. So that was $414. Okay, this was $42. No, $42. $420, and then this would be whatever that multiplies to. Okay. If you think about it, the North Stands are in the South Sun hitting it, so they got a lot thirstier than now. Must have been a day game, you know. Yeah. Okay. Now in the book they came out with 1986-25. I haven't checked them. And then on the West Stands, they 29 bags of peanuts at $2, so that would be $58 plus $360 for the sale of hot dogs, and then 190 times 275, whatever that comes out to. They claim it's $940.15. That's not right. 50 cents. Okay. I said 15. I said that can't be. Okay. All right. I didn't check their math. So that's how you do it. Okay. Now, that's fairly reasonable way to do a calculation. Okay. And if you know what these things are, yeah, that's making sense. Well, this represents how you do matrix multiplication. Okay. I'll give you the algorithm first, and then we'll see this really does work. So here's the definition of matrix multiplication. If A is some matrix, Aij, okay, M by N matrix, okay, and B is a matrix, Bij, oh wait, yeah, they say it the same way. I want to make sure they did, okay. It is an N by P matrix. That's an N by P matrix. Whoa! This one's M by N, that one's N by P. Okay? Well, it's sort of like what we got here. This is a 3 by 3, and that one's a 3 by 1. So it just happens to be this N and that N are the same ends. That's an N there, not an M. Okay. Then you can multiply. Okay. Then the product as is a thing result from multiplication. AB, and that's how we usually write it. AB is an M by P matrix. Okay. Now here's what we do. If you're trying to multiply two matrices, A and B, here's what's required. It's absolutely necessary for you to multiply. When you list this as an M by N, this is an N by P, these two interior numbers have to be identically the same. 3 by 3. Doesn't matter what the first one was, but the last one being 3, this has to be a 3 by something. This happens to be a 3 by 1. So the number of columns in this one has to equal exactly the number of rows in this one. Because you're doing this. So the number of columns here has to equal exactly the number of rows there. Has to. And since it has to be equal, then your product, the result of that, just throw those away, and it's an M by P. Okay? Now this happened to be a 3 by 1 also. That's just because M was 3 and your P was 1. That's what didn't matter that was square. This could have been a 4 by 3. That would have worked. If you had 4 sands, add a East sands as well. That could have been a 4 by 3 times a 3 by 1. That would have given you a 4 by 1. Okay? So that works. Okay? And that's how that's what's required. Okay? And then of that product, AB, that's going to be some Cij. Okay? Okay, just to give it a different name. Where, and here's what has to be true about Cij. Okay? That's going to be a summation. Are y'all familiar with summation symbols? K equal 1 to N, okay, of A, I, K, B, K, J, okay. All right. And what that means is, that's so aggravating, that for the first entry is A11 times B11 plus, okay, sorry. Let me change these. I could have just, I put it in the wrong place. I1, let me get it right this this time. Okay. I'm trying to make a distinction between i's and 1's. B 1j, okay, plus a, see the k is counting 1 to n, so the k is the interior 1, b I 2, a I2, b 2j, plus a I3, b 3j, plus dot 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 up to a sub I n, no, yeah, n, b, n, k. All right. That's what we mean. You do this kind of motion. You go across this way, down that way, and you multiply element by element by element. Okay. Now, to me, this is correct. If I think through it, I say, yeah, that is, yeah, everything's right about that. But this says nothing. This doesn't give me a good insight on what to do. So I'm going to show you my way of doing this, and this is how we're going to do example 4. Now, if you have some other way using what they have here or anything else, that's not what I want. Okay. All right. It says find the product AB, that's what we're looking for, when A is equal to -1, 3, 4, -2, 5, 0. Okay. B is -3, 2, -4, 1. Okay. Question 1. Can we add those two matrices? No. Can we subtract those two matrices? No. Can we multiply the two matrices? Maybe. Here's how you tell. What's the size of A? 3 by 2. What's the size of B? 2 by 2. Are the middle numbers the same? Yes. You can multiply. What's the product going to be? The outside numbers. 3 by 2. Okay? So it's going to be 3 rows, 2 columns. Okay? Now, here's how I do it. I go 1, 2, 1, 2, 1, 2. There's my 3 rows, 2 columns. Right? Now I've got to find the numbers that fit in there. Okay. Here's what I do. What is the name of this place? The subscripts. 1, 1, right? You have 2. 1 for row, 1 for column. That's the 1, 1. So how you get the 1, 1 entry there, you take the first row of A and the first column of B, multiply and add as you go. Okay? So this would be 3.
So you multiply now 3.
Multiply
So that's
-12. 3 minus 12 is -9. That's your entry right here. -9. Okay? Got it? First, see what size it is. First, can you multiply? Those two interior, the number of columns here has the equal number of rows there. If it does, wipe them out. Your answer is going to be, you already know, if those are the same, you can multiply, your answer is going to be the outside, 3 by 2. Since you know 3 by 2, lay it out. 3 rows, 2 columns. Okay? And then I look at this one, that's the 1, 1. So I do first row by first column. Multiply and add as you go. Okay. What's the name of this one? The indices of this one. 1, 2. So you do first row, second column. That would be -2 plus 3. 1. Okay, that will be a 1. Do you see how this works? Okay. What is the name of this one? 2, 1. Always name row first, column second. So this is the 2, 1 entry. So I do the second row here by the first column here. 2, 1. And that would be negative 12. Yes? Second? Negative 12 plus 8. Negative 4. Yeah, negative 4. Don't forget your sign. Okay. Minus 4. Okay. What's the name of this one? 2, 1. No, 2, 2, 2. So we'll do the second row here, second column here. At?
8.
Okay, we need to do the back of few grades in math here. Okay, yeah. This will be 8. 8 minus 2 is? 6. All right, we got it. All right. What's the name of this entry? 3, 3, 1. So you do third row here, first column there. Negative 15, right? All right. And what's this last entry? 3, 3, 2. Okay? So it'll be the third row here, second column here.
Is that negative 5 or 5?
Looks like a 5 to me.
10.
10? Okay, and that would be 10. Okay? Now, the thing about matrices, the operations are simple. They're just tedious. There's lots of little things to do and keep up with them all, and it's so easy for one little error to throw you completely off, but that's the rest of it is pretty easy. Let's see what we get. Negative 9, 1, negative 4, 6, negative 15, 10. Yes. Okay. They have a little blurb here on Arthur Cayley, British mathematician credited with giving abstract definition of a matrix. A lawyer by profession, he began groundbreaking work, blah, blah, blah. So anyway, I'll let you read that. There's some other people mentioned here, two American mathematicians, Benjamin Peirce and Charles Peirce, his son. So there's 3 potential paper topics, or you could pick anything in there like work on theory of transformations. What's that? That could be a paper topic. Development of determinants. That's going to be later, but so there's lots of little possibilities there. The book is okay for getting ideas for your paper, but you have to go outside the book to get your sources. Okay. Any questions on multiplying matrices? This, to me, is the easiest way to do it. First, make sure you can multiply them. Those interior numbers have to be the same. If they are, you can multiply. Throw them away, and then the exterior numbers will be the size of your result. Go on and put down exactly that size, and then do each entry at a time. The row is going to be which row in A, the column will be the column in B. Okay? And do the multiplication that way. This is called the multiplication of matrices as opposed to scalar multiplication. My goodness. Are we almost out of time?
No, we only have 4 minutes.
4 minutes? Okay. All right. I think the top of page 44 is exactly what we were doing, so I don't see any reason to rehash that unless you think that would be beneficial. But that's exactly what we were doing. Let's do the little discovery. That shouldn't take long. Okay? So here it is. Let's go to a clean page. I don't think I need it, but just in case, just to keep from getting crowded. Here's matrix A. 1, 2, 3, 4. Very creative matrix there. Okay? And here's matrix B. and this is 0, 1, 1, 2. Okay? It says calculate A plus B. Can anyone do that almost in your head? Oh, wait. First, can you add those two?
Yes.
Yes. What do you get?
You get 1,
1, 3. Second? 4,
4,
6. Got it. Yeah, you can add it. How about B plus A? Can you do that? What would it be? 1, 3, 4, 6. Yeah. So addition of two matrices is commutative. Doesn't matter which order you do it, it's the same answer, right? All right. Let's do, can you do A times B? Second? Yes. Okay. What will its answer be? What size? 2 by 2. Okay. So let's start with the first entry here. What's its address? 1, 1. So you do the first row of A times the first column of B. And that would give you 2. Okay. 0 plus 2 is 2. Good. All right. What's the address of this one? Oh, and it doesn't matter which order you do these. You can do any order, but be sure you get the address. What is the address? 1, 2. So you do the first row of A times the second column of B. And this will be 4. Okay. That would be 5. Do I have to stand up, or can you do the next one?
That's going to be 2. 1, that's going to be 0. It's going to be 4.
4. Excellent. Okay. The last one?
It's going to be 3. 2, 2. 3, 1 give you 3. 4, 2 give you 8. 8 and 3 give you. He said 11.
11. Perfect. Okay. He said, she said. Okay. Now,
Yeah, I did this really finish.
yeah. Can you do BA? Yay or nay? Yay. Okay. Yay. Okay. So I'm going to write A over here again. 1, 2, 3, 4, just so it's easier to see. And what size will this be? 2 by 2. Okay. And what would be the first entry of that? 2. Wait, is it?
No, I don't know. It's gonna be. Actually, it is.
Huh?
It is 2.
Okay. It's the 1, 2 entry. Now this is A. So it's first times this, right?
Oh.
Oh!
It's 3.
3. Okay. Trying to sell me a bill of goods. 3. Okay. All right. He's going to just put a 0 at the end. Okay. Next entry
Next entry is gonna be 2, 2.
is what?
It's gonna be 1, 2.
1, 2. So it'd be
0,
4. Good. Next entry. 2, 1. Second.
5. It's 1.
Okay.
Oh,
2,
no, it's
1.
1, 2. I'm doing 1, 1. So it's. I'm doing 2, 1. I'm sorry. It is 2, 1, right?
It's 2, 1. Yes.
Yeah, 1, 1. Oh, 6. Yeah, 6.
And what?
6 plus 1, that gives you, so.
7. All right. All right. And the last entry.
Last entry. Ooh. You do that one.
I'm almost wanting to just to get out of here. Okay, what would that be?
It's 2, 2. Okay, 2, 2. There's gonna be 1 times 3 give you 3. 2 times 4 give you. That's what it, oh no, we do. Alright, it's 1 to give you 1. No, 1 to give you 2, and then 2, 4 give you 8, and then 8, 2.
What's that?
8 and 2.
Is?
Give you 10.
10. All right. Goodness gracious. Okay. Now, the question is, we saw the addition of two matrices is commutative. It doesn't matter which order you add them. How about multiplication of two matrices? Not commutative. Multiplication of two numbers, no problem. But two matrices, no. You cannot multiply two matrices in any order and expect to get the same answer. Can't do it. Adding, yeah, no sweat. Multiplying, no. Except in some very special cases. When the commuted forms give you the same answer, you have some very special matrices on hand. We're not going to get there yet, but we'll get there soon. But in general, two matrices, if you can multiply them, are not commutative. Many two matrices you can't. Only if they're square can you multiply them both ways. Because if this is a 3 by 2 and that's a 2 by 3, a 3 by 2 and a 2 by 3, yeah, those are multiplied. Oh, those, yeah, they'll work too. But if this is a 2 by 3 and this is a 3 by 4, then they won't do it. You know, you can't even multiply. So some you can, but others you can't. Okay? But in general, the commuted form will not be the same. Will not be the same. All right, we'll pick up next time in example 5. And let me give you a few homework exercises to do.
Scholarship,
What's that?
the scholarship we was talking about, it's not a similar thing. It's for your senior and junior year scholarship.
Okay,
It's for if you're going
but they don't have some. The scholarship money is for junior and senior years.
Yes.
Okay, but there's summer programs, aren't there?
No, this one, the scholarship was talking about, this one doesn't have something.
It does not have a summer program. Okay, I hadn't read the details.
I just read it.
Okay. Well, if you were going to A&M and majoring in teaching,
Yes.
yeah, then they would pay your scholarship.
They will pay it and then you have to commit to teaching at least 2 years after it.
Yeah.
If you don't, you gotta pay them back. They say with any desired interest, they're gonna make their own interest. So you never know. They're gonna teach you with 100% interest.
Yeah, for real.
All right. Homework exercises here will be 1 or 3. Any of the odds 5 through 11, 13 or 15, and then you can start doing 17 through, wow, I think you can go up to 29 if you choose. We'll do the rest of them next time.
Up to 29.
Huh?
Up to 29.
Up to 29. Yeah. No, up to, yeah, that's what I said, 29.